U.S. surveillance satellites detected a mysterious signal in the 1960s. Flashes of gamma rays, the highest energy form of light, were expected from nuclear tests on Earth, but not from deep in space. Soviet and U.S. researchers joined forces to investigate these powerful bursts, using a variety of space missions, including Helios, a spacecraft that orbited the Sun, and the Venera probes, which traversed the inner solar system. Most of the bursts hailed from massive stars exploding in supernovae. But in 1979, scientists encountered an extraordinary flash from a galaxy near the Milky Way. By 1992, researchers had a theory for what could have created such a powerful signal: a magnetically amped up neutron star. They gave it a name: magnetar. Neutron stars are the densest form of matter. They form when the core of a star implodes and shrinks to the size of a city. This amplifies the star's pre-existing magnetic field. But the flash captured in 1979 pointed to something even more magnetic than a normal neutron star. Scientists proposed that during the early life of some neutron stars, their molten guts churn enough to create dynamos, swirling currents that create powerful magnetic fields. A magnetar's magnetic field is about 1 trillion times clingier than refrigerator magnets and 1,000 times more powerful than an average neutron star. Researchers have been waiting for the perfect opportunity to study these extreme neutron stars. That event finally came last year on April 15, 2020, when sensors in space and on Earth detected an unusual gamma-ray burst from Sculptor, a nearby galaxy. The brevity of this signal, mere milliseconds, suggested that it came from an eruption on the surface of a magnetar. Just as movements in the Earth's crust caused earthquakes, neutron stars can rupture. In magnetars, starquakes result from grinding and magnetic stresses in its hard outer crust. The rupture releases an explosion of charged particles, or plasma, that in turn generates a beam of gamma-ray photons. As the first giant flare in 16 years, this event allowed researchers to use recent technology to answer long-standing questions about magnetars. They calculated the strength of the flare and found it packed 100,000 years of the sun's energy in its quick burst. Based on the timing of the gamma-ray burst, they were also able to confirm that the plasma was let loose near the pole of the magnetar. In the wake of the burst, researchers have searched for overlooked magnetar events in astronomical back catalogs. They found 3 additional bursts from galaxies near the Milky Way, bumping the total number of recorded magnetar flares to 7. Researchers think this means that these flares are more common across the universe than previously thought, and that it's relatively easy for neutron stars to be born as magnetars. It also suggests that distant magnetar eruptions might explain other mystifying phenomena, such as fast radio bursts. Scientists are eager and ready to detect the next burst that will send a shockwave through the field of astronomy.